for A negative, and then the value of X. To make the math easier, we can assume the 5% rule, where the dissociation of X is so small compared to the amount of the original 0.1 that it's being neglected. That the amount of A negative from the original source is being neglected, and so we toss it out. The 5% rule says that if the dissociation is less than 5%, we're allowed to just toss out the math and make it a little easier. You can certainly solve using quadratic equation. But if this is so small compared to the original number, toss it out. 0.1 times x over 0.1 simply gives us the value for x. If x represents the hydronium ion, H3O+, we can simply hit negative log of that original Ka, and we've got the pH of our solution. And let's take a peek ahead and show what they've done. They're testing the 5% rule, which I had mentioned. The 5% rule says that if the amount of X, indeed, the amount dissociated, is less than 5% of the original concentration, we are indeed allowed to toss out the value of X. So this slide is just proving to us that Ka, which comes out to be the concentration of hydronium ion, does indeed fall within the 5% limit, and so our math is valid. We'll toss out the minus x and plus x and make the math simpler. Negative log that Ka value, and we'll come up with our pH, 4.74 pH units. So we found the equilibrium concentration of the acid, drop that out. pH is negative log of the hydronium, and there's no units on pH, it's simply 4.74, which makes sense. We're in an acid range, a weak acid, so that lies certainly within the realm of possibility for a weak acid's pH. So final answer, the pH is given to us as 4.74 pH units. We'll try another. What is the pH of a buffer that is 0.14 molar HF, giving me a pKa value? P is just this negative log function in math talk, and 0.071 molar Kf. The equilibrium comes from the weak acid. Here's what we know. Alrighty. HF is a weak acid in equilibrium with H positive and F negative. You can certainly show the water making hydronium or HF making hydrogen ion. I think this is just a little simpler. We have an initial concentration of 0.14 molar HF. We have an initial concentration from the common ion. Potassium fluoride is the source of the fluoride ion, 0.071 molar, and 0 as the initial concentration of our acid ion hydrogen. Reactants get used, products get made. All 1-to-1 stoichiometric ratios. So at equilibrium, 0.14 minus x represents the concentration of the acid. The value of x itself represents hydrogen ion. And 0.071 plus x represents the concentration of fluoride. The Ka value is 10 to the negative 3.15. Taking the inverse, P is negative log, so the inverse of that is 10 raised to the negative pKa, to just turn the pKa into Ka, 10 raised to the negative 3.15. So the equilibrium expression, products over reactants. Ka is equal to the concentration of the product, hydrogen, times the concentration of the fluoride over the concentration of the hydrogen fluoride acid, HF. We can assume, and it's always wise to just do this once and then check, if we are obeying the 5% rule and the X comes out 5% less than 0.14, the original amount of the acid, we can toss these out. So it's always worth trying that. So let's take a look, simplify some things first. 10 raised to the negative 3.15 is how I turn pKa into Ka. So that's 7.0, and I'll just round, 7.08 times 10 to the negative fourth. Alrighty. And I can certainly distribute through. You guys aren't scared of algebra, I know, and pull out the quadratic formula. Or we can test the 5% rule. Solve for x, and let's compare the value of x to the original 0.14. And let's just do that. Let's toss these out, and then we'll check. If it doesn't work, we'll come back and do the long math. So in other words, just kind of working this through, 7.08 times 10 to the negative fourth times 0.14 is equal to 0.071x. Just distribute the top, simplified the top, brought this 0.14 to the left-hand side. So this is what we have so far. So times 0.14. So I get 9.91 times 10 to the negative fifth is 0.071x. Divide that by 0.071, and I get the value of x. 0.014 molar is my value of x. Before we go and hit negative log and find the pH, let's check the 5% rule. X came out to be a value of 0.0014. The original concentration was 0.14. What percent dissociated? All right. The 5% rule says that if the dissociation was so small, insignificant to the value, we're allowed to toss it out. So this original concentration divided by 0.14 expressed as a percent gets us quite a small number, 0.997% dissociation, falls well beneath the 5% rule. So the math was valid. We're allowed to toss out the x and simplify the algebra. So I checked the 5% rule. If it were greater than 5, I got to back up and do the algebra. I like to toss it out first, check it, it's usually good. Now, to finish the problem, pH is negative log of that hydrogen ion value that we found. And the value of x was 0.0014. So now on my screen, I hit negative log 0.0014 molar, and we get a pH of our solution 2.85 as the pH. Coming back to the original question, what's the pH of a buffered solution between a weak acid and a conjugate base with the common ion here, potassium fluoride? The fluoride is the common ion between these two, and that becomes the starting value in the ice chart. We made more fluoride. We made hydrogen iodide, so those values were positive. HF got consumed. We tossed these values out and simplified with easy algebra, checking that our math was indeed valid. Let's look ahead and see if we got the problem right.